On August 11, 2003, Paris entered a night that would become one of the most important heat health warnings ever recorded. The daytime heat had been brutal, but the deeper danger arrived after sunset, when streets, walls, roofs, and apartments refused to cool. At official stations, minimum temperatures stayed above 25.5 degrees Celsius for 2 consecutive nights, an extraordinary event for Paris. Inside the city, the temperature map was even more disturbing. Some neighborhoods remained measurably warmer than others through the night. Researchers later compared where older residents died with where nighttime heat lingered, and the pattern was difficult to dismiss. A difference of only about half a degree in minimum temperature was associated with roughly twice the odds of death in the study group. The lesson was not simply that Paris had become hot, it was that parts of the city had lost their ability to release heat. Concrete had stored the day. Narrow streets had restricted airflow. Buildings radiated energy back into rooms long after the sun disappeared. Above all of it, the atmosphere was unusually stable, limiting the vertical motion that normally helps dilute heat, moisture, and pollution. This is the image now haunting cities across a warming planet: a hot surface below, a stable atmosphere above, and millions caught between them. But one popular explanation is too simple. There is no single thermal inversion belt physically descending over every major city on Earth. There are several kinds of inversions, several forms of stagnation, and several urban processes that can produce the same frightening result. And the most dangerous part is not always the afternoon maximum shown on a weather app. Often, it is what happens after midnight. When the body expects relief, the city keeps returning yesterday's heat, while the air above becomes too stable to efficiently carry it away. That combination is changing the geography of urban risk, and new observations suggest the atmosphere itself is changing in complicated ways. A global radiosonde analysis found surface-based inversion frequency increased from 1989 to 2019, but trends varied sharply from place to place. So the real story is not an expanding wall in the sky. It is a growing overlap between extreme heat, urban storage, and atmospheric stability. When those systems align, a skyline does not become a literal pressure cooker. It becomes something more scientifically precise and equally dangerous. The city becomes a reservoir of heat beneath an atmosphere that has temporarily lost much of its capacity to ventilate the surface. That distinction matters because a temperature inversion is not simply hot air sitting over a hot city. Under normal conditions in the troposphere, temperature usually decreases with height. An inversion reverses part of that profile. For some vertical layer, temperature increases with altitude. That warmer layer can create strong stability and resist the rising motions that normally mix the lower atmosphere. Meteorologists separate inversions by how they form. A clear, calm night can cool the ground rapidly, producing a shallow radiational inversion near the surface. Mountain basins can collect dense cold air and create valley inversions. Warm air can slide above colder marine air, and broad high-pressure systems can generate elevated subsidence inversions as sinking air compresses, dries, and warms. That last mechanism is especially important during prolonged heat. Large ridges of high pressure encourage air to sink over a vast region. As the air descends, compression warms it. Cloud formation can be suppressed, rainfall can disappear, soil dries, sunlight becomes relentless, and the same air mass can remain over a region for days. The atmosphere becomes capped. This is the physics behind many so-called heat domes. The phrase can sound like a transparent lid, physically trapping heat at street level, but the reality is dynamic. Persistent high pressure, subsidence, clear skies, weak ventilation, dry soils, and repeated solar heating cooperate to maintain extreme temperatures. An inversion may be part of the structure, but it is not the entire heat wave. Cities then modify that regional event from below, replace moist soil with asphalt, tree canopy with roofing, and open land with masonry, and the surface energy budget changes. Natural landscapes can spend a large fraction of incoming energy evaporating water. Impervious urban surfaces have less moisture available, so more energy is converted into sensible heat or stored inside construction materials. During daylight, roads and walls absorb solar radiation. Some surfaces can become dramatically hotter than the surrounding air. The important consequence arrives later. After sunset, vegetation can cool rapidly, but concrete, brick, stone, and asphalt continue releasing energy they accumulated for hours. The city begins paying back its thermal debt when residents most need recovery. That is why the atmospheric urban heat island is often especially pronounced at night. In the United States, EPA summaries place typical urban-rural air temperature differences at roughly 1 to 7 degrees Fahrenheit during the day and 2 to 5 degrees at night. The exact number varies with climate, weather, city size, vegetation, moisture, and urban form, but the nighttime pattern is crucial. A dense downtown does more than contain dark surfaces. Its geometry changes the exchange of energy with the sky. Tall buildings reduce the portion of cold sky visible from the street. Radiation leaving one wall can strike another wall instead of escaping freely upward. This reduced sky view factor slows radiative cooling inside urban canyons. Buildings also reshape wind, accelerating flow in some places, while creating sheltered zones and recirculating eddies in others. Street orientation, building height, roughness, wind direction, and stability determine whether an urban canyon ventilates well or traps stagnant air. Now add waste heat. Air conditioners reject indoor heat outdoors, while vehicles, industry, refrigeration, data centers, and other activity add more. During severe heat, those extra fluxes enter an urban energy system already struggling to cool. The atmosphere above the city is trying to respond. In strong daytime sunshine, warm surface air usually becomes buoyant, turbulence grows, and the planetary boundary layer deepens. Rising thermals mix heat and pollutants through a larger vertical volume. If winds are adequate, that mixed air is also transported away. A healthy afternoon atmosphere can be surprisingly effective at ventilation. But persistent high pressure changes the odds. Subsidence aloft can strengthen stability above the mixed layer. Winds may weaken, the boundary layer may stop deepening as much as it otherwise would. In mountain valleys, coastal basins, and heavily enclosed urban regions, topography can compound the problem. The effective volume available for dilution shrinks. This is where heat and air pollution begin to interact. Cars, power plants, industrial sources, solvents, combustion, and other activities release gases and particles into the lower atmosphere. A stable layer does not magically create those pollutants, but it can reduce the rate at which they disperse vertically. Concentrations near breathing level can therefore rise under some inversion conditions. One study using temperature profiles over Hamilton, Ontario, found nighttime inversion episodes were associated with substantial increases in nitrogen dioxide and fine particulate matter. The exact response differed by pollutant, by daytime versus nighttime conditions. A reminder that inversion chemistry is not a simple lid and smoke cartoon. Emissions, sunlight, mixing, humidity, wind, and chemical reactions all matter. Summer introduces another threat, ground-level ozone. Unlike soot pouring directly from an exhaust, ozone is largely a secondary pollutant. Nitrogen oxides and volatile organic compounds react through sunlight-driven chemistry. High temperatures can accelerate aspects of the chemistry, while stagnant conditions allow precursors in ozone to persist over a region. This is why extreme heat can arrive with air that looks deceptively clear. The sky may be blue, there may be no visible smoke plume, and yet ozone exposure can climb. Heat attacks the cardiovascular and thermoregulatory systems, while ozone irritates the respiratory system. When wildfire smoke is added, the compound hazard can become even more severe. The Russian heat wave of 2010 demonstrated how ugly this combination can become. Persistent high pressure produced extreme temperatures and drought, while wildfires sent smoke across western Russia. A subsidence inversion associated with the high pressure pattern helped suppress vertical dispersion. Moscow did not merely endure heat. It endured heat inside an atmosphere burdened by smoke and stagnation. Yet, inversions do something that seems contradictory. A classic radiational inversion often begins because the ground cools rapidly at night. How can a process built on surface cooling be blamed for dangerous urban heat? The answer is that different inversions operate at different heights and different times, and the most important health signal is not simply whether an inversion exists. On a clear rural night, strong surface cooling can create a pronounced inversion because the ground becomes cold. In a dense urban core, stored heat can keep the surface warmer, sometimes weakening the near-ground nocturnal inversion locally, while the city still remains dangerously hot. At the same time, an elevated stable layer, or regional subsidence inversion, may persist above the urban boundary layer. This is why phrases like thermal inversion belts descending over cities can mislead. The vertical temperature profile above downtown Paris may differ from the profile above a rural field only tens of kilometers away. The city itself can alter turbulence, stability, and boundary layer depth. There is no single ceiling height that behaves identically across an entire metropolitan region. Researchers map these invisible structures with radiosondes, towers, satellites, remote sensors, and weather models. Profiles reveal stable layers, while surface networks and thermal imagery show which neighborhoods and materials are storing or releasing heat. A crucial measurement problem follows from this complexity. Satellite land surface temperature is not the same thing as the air temperature a person breathes, and neither alone captures radiant heat, humidity, or indoor exposure. A black roof may appear scorching from space, while a shaded street nearby has similar air temperature but far lower radiant load. Heat maps are powerful, but only when interpreted with the variable they actually measure. The maps can be startling because a single official weather station cannot represent a whole city. A shaded airport sensor over grass may report one temperature, while the treeless neighborhood surrounded by dark roofs, wide roads, and low ventilation experiences a very different radiant environment. Even two streets a kilometer apart can produce meaningfully different heat exposure. Paris, after the 2003 disaster, became one of the clearest examples. Researchers used satellite-derived thermal indicators and residential data for older people who died during the heat wave and matched controls. The strongest associations appeared with nighttime minimum temperature. During that event, fractions of a degree mattered because the entire population was already near physiological limits. Night is when a healthy human body should begin reducing accumulated heat strain. Core temperature can fall, the cardiovascular system receives a partial break, sleep becomes possible, and dehydration can be corrected. When bedrooms remain hot through the night, especially without air conditioning, that recovery window narrows or disappears. Heat becomes dangerous through physiology, not through the thermometer alone. The body moves heat toward the skin by increasing blood flow. Sweating allows evaporation to remove heat, but dehydration reduces that capacity. High humidity makes evaporation less efficient. Certain medications and chronic diseases interfere with thermoregulation. Age changes thirst, circulation, mobility, and the ability to recognize danger. The result is cumulative. A person may survive one brutal afternoon because the body compensates. If the night remains hot, the next day begins with incomplete recovery. Add another afternoon, then another tropical night, and the same temperature can become more dangerous because physiological strain has been carried forward. Recent research is increasingly focusing on exactly this day-night compound exposure. A 2026 global analysis of heat stress found that hazardous heat has expanded spatially since 1950, and that the hottest nights have been warming faster than the hottest days in the dataset. That matters because nighttime warming attacks the recovery phase that urban populations depend on. This is the evidence that gives the dramatic idea of expanding heat belts a defensible core. The footprint of dangerous heat is expanding. Surface-based inversion frequency has shown a global increase in one multi-decade radiosonde analysis. Some regions, such as the Po Valley, have studies projecting more warm season inversions and stagnation under future climate scenarios. But those findings cannot be collapsed into one universal claim. The inversion study, covering 493 radiosonde stations, found no spatially consistent trend in every inversion characteristic. Frequency rose overall, while inversion depth declined and strength varied. Climate change modifies atmospheric stability differently by region, season, elevation, moisture, circulation pattern, and surface type. The Po Valley shows why geography matters. Northern Italy is bordered by major mountain ranges, creating a basin-like environment where weak ventilation and stable atmospheric conditions can allow pollution to accumulate. Climate projections for the region have suggested increases in warm season inversion and stagnation conditions, but a mountain-enclosed industrial plain cannot simply be treated as a template for London, Singapore, Phoenix, or coastal Tokyo. Delhi presents another configuration. Severe pre-monsoon heat, intense solar radiation, dust, urban emissions, regional transport, humidity shifts, and changing boundary layer dynamics interact over one of the world's largest metropolitan regions. Recent modeling of Delhi found that moist and dry heat waves can produce different ozone behavior, emphasizing that hot and stagnant is not a single atmospheric state. Coastal cities add sea breezes and marine layers. Desert cities add extreme sensible heat. Tropical cities may face humidity that limits human evaporative cooling, while high-latitude cities may be less acclimatized. The hazard is global, but the physics remains local. That is why researchers use local climate zones instead of treating a city as one temperature. High-rise districts, low-rise neighborhoods, industry, tree cover, bare soil, water, and paved surfaces each exchange heat and momentum with the atmosphere differently. A tree-lined block can be cooler because leaves intercept solar radiation, and water evaporating through vegetation consumes energy. A park can function as a local cool island. A highly reflective roof can absorb less solar energy. A shaded sidewalk can reduce radiant heat exposure dramatically, even when the official air temperature changes very little. But every intervention has limits. Trees need soil volume, water, maintenance, and years to mature. Reflective surfaces can lower absorbed solar energy, but may alter glare or redistribute radiation at pedestrian level if designed poorly. Green roofs help specific buildings and neighborhoods, but cannot erase a regional heat dome. Cooling centers only protect people who can reach them. This is where inequality becomes part of atmospheric physics. The lower-income neighborhoods in many cities have less tree canopy, more impervious surface, older housing, limited access to air conditioning, and residents whose work may require outdoor exposure. Studies across major U.S. cities and broader reviews have found systematic disparities in heat exposure and adaptive capacity. The same inversion can therefore produce different outcomes across a few subway stops. One household sleeps in an insulated apartment with efficient cooling and backup power. Another lives on the top floor beneath a dark roof, beside a 6-lane road, with windows that must remain closed because outdoor air is polluted. Meteorology sets the hazard. Urban inequality determines part of the dose. Electricity becomes another hidden dependency. Heat increases air conditioning demand precisely when transformers, transmission equipment, and generation systems are under stress. If the grid fails during a hot, stagnant night, thousands of buildings can abruptly lose their main defense. The thermal mass that once slowed daytime warming can then become a source of indoor heat after sunset. Air conditioning creates a spatial paradox. It can be life-saving indoors while rejecting heat outdoors and raising electricity demand. The answer is not to abandon cooling, but to make it efficient, resilient, and paired with measures that reduce urban heat itself. The most dangerous urban heat is therefore a system's failure rather than a single meteorological event. The regional atmosphere delivers an extreme air mass. The city stores additional energy. Urban geometry modifies wind and radiation. Stable layers suppress some forms of ventilation. Pollution can accumulate. Buildings determine indoor exposure. Infrastructure determines whether residents can escape. Seen this way, the phrase pressurized pressure cooker becomes unnecessary. Atmospheric pressure near the surface is not building to explosive levels inside the city. What is building is heat content, radiant load, physiological strain, pollutant concentration, and dependence on mechanical cooling. Those are measurable hazards, and they can be mapped. The first maps should begin with nights. Daytime satellite imagery is visually dramatic because asphalt, roofs, and industrial surfaces blaze on thermal images, but the neighborhoods that stay hottest after sunset often reveal more about human risk. Minimum temperature, indoor temperature, humidity, wind, radiant heat, and duration can matter as much as the afternoon maximum. Public health systems are beginning to reflect this. Heat warnings increasingly consider more than a single peak temperature, while heat health action plans incorporate vulnerable populations, communication, surveillance, healthcare readiness, cooling access, and long-term exposure reduction. The World Health Organization's updated 2026 guidance treats extreme heat as a growing public health threat intensified by climate change, urbanization, and aging populations. The urgency is not theoretical. During the European heat crisis of June 2026, the WHO regional office reported emergency services under severe pressure, including record life-threatening ambulance calls in London and major increases in emergency medical demand in parts of France. The event arrived in a continent already warming faster than the global average. At the global scale, the trend is even harder to ignore. Heat waves are becoming more frequent, longer, and more intense in many regions as the climate warms. The background temperature from which every local heat island begins is rising. A 2-degree urban penalty applied to a hotter baseline pushes more nights across thresholds that once were rare. Urbanization adds another moving target. More people are living in cities, more land is being paved, and metropolitan regions are expanding into climates already vulnerable to extreme heat. The question is no longer whether individual cities possess heat islands. It is how urban form, regional climate change, and atmospheric circulation combine as billions of people become more urban. There's a temptation to search for one futuristic solution. Reflective megastructures, artificial clouds, citywide air conditioning, or predictive AI systems. The physics points toward something less glamorous. Cities need many small interventions applied at scale: shade, vegetation, reflective materials, permeable surfaces, ventilation paths, efficient buildings, reliable power, and targeted protection for high-risk residents. Cool roofs are one of the simplest examples. By increasing solar reflectance and, depending on the material, thermal emittance, a roof can absorb less energy and transfer less heat into the building. EPA summaries report meaningful reductions in indoor maximum temperatures for some unconditioned buildings and lower cooling demand for conditioned buildings. Trees attack the problem differently. Shade prevents solar energy from reaching people and surfaces in the first place, while evapotranspiration converts energy into latent heat rather than simply raising surface temperature. Yet a 2026 global analysis found that existing tree cover, while substantially reducing potential urban heat island intensity, could offset only a modest fraction of projected mid-century climate warming. That result is important because adaptation cannot substitute for climate mitigation. A city can repaint roofs, plant trees, redesign streets, and save lives, but if the regional background climate continues warming, the target keeps moving. Urban cooling reduces the local penalty. Emissions reductions determine how rapidly the baseline itself continues to rise. Ventilation corridors can help, but only when designed around local meteorology. Open pathways aligned with prevailing winds may improve exchange, while poorly placed high-rises can create sheltered zones. No universal geometry guarantees cooling because wind, stability, topography, and street orientation differ. Cities also need better measurements. A single airport station should not decide which neighborhood receives emergency resources. Dense sensor networks, mobile measurements, satellite data, building information, health records, and atmospheric profiles can reveal where exposure actually concentrates. The invisible ceiling matters, but so does the invisible map of vulnerability beneath it. Forecasting systems can then combine synoptic weather with neighborhood conditions. A heat dome approaching a city with high soil moisture may behave differently from one arriving after drought. A windy heat wave may ventilate pollution better than a stagnant one. A dry 42-degree afternoon and a humid 36-degree afternoon can impose different physiological loads. The same sophistication is necessary for inversions. Forecasters should distinguish a shallow nocturnal surface inversion from an elevated subsidence inversion and from general low wind stagnation. They should track boundary layer depth, mixing, and pollutant chemistry, rather than using the word inversion as a universal explanation for every bad air or extreme heat episode. That scientific precision does not weaken the warning. It strengthens it. When residents understand that the real danger is cumulative heat plus failed nighttime cooling, public advice can focus on the hours that matter most. When planners know which neighborhoods retain heat after sunset, resources can be placed where exposure persists longest. It also explains why a city can remain dangerously hot even after the synoptic heat wave begins weakening. Buildings and pavement have thermal inertia. Indoor spaces can lag behind outdoor temperature changes. Humidity can remain high. Electricity systems can remain strained. Health impacts can peak after several days of accumulated exposure rather than at the exact moment of maximum temperature. This delayed response was visible in major historical heat disasters. Mortality curves did not simply mirror one afternoon thermometer reading. They reflected accumulated stress, nighttime conditions, age, housing, social isolation, health status, and access to cooling. The atmosphere began the emergency, but the city determined how long the emergency remained inside people's homes. That is the real meaning of an invisible ceiling over a modern metropolis. Sometimes the ceiling is a measurable inversion layer. Sometimes it is a broad zone of atmospheric stability. Sometimes the more important barrier is not overhead at all, but a street canyon with weak wind, a sealed apartment or a roof radiating stored heat into a bedroom. The phrase thermal inversion belt suggests a moving object, something that could be watched on radar as it expands from city to city. Reality is more unsettling because it is distributed. The risk emerges from multiple systems changing at once: a warming climate, more dangerous nights, growing urban surfaces, persistent high-pressure episodes, and unequal access to cooling. Observations do show reasons for concern about inversion behavior. The multi-decade radiosonde record found an overall increase in surface-based inversion frequency, and some regional climate studies project worsening warm season stagnation. But the atmosphere has not organized those changes into a uniform global belt. Spatial trends remain heterogeneous, and local circulation can strengthen or weaken the effect. What is expanding more clearly is human exposure to dangerous heat. More regions are experiencing extreme thermal stress, compound day-night heat events are becoming more important, and cities impose a local thermal penalty exactly where populations are densest. The risk does not require a new atmospheric phenomenon. Familiar physics operating on a warmer planet is enough. Return to Paris in August 2003. The catastrophe was not produced by one mysterious ceiling. It was produced by an exceptional heat wave meeting an old, dense city, hot nights, vulnerable residents, air pollution, and buildings that could not shed accumulated energy quickly enough. The disaster transformed how Europe thought about heat. More than 2 decades later, the instruments are better. Satellites can identify hot surfaces block by block. Weather models resolve urban canopies with increasing detail. Sensors can map temperature while vehicles move through neighborhoods. Health systems can issue targeted alerts. Researchers can profile the atmosphere above a city and watch the stable layers form. But technology cannot cool a street by describing it. The fixes remain physical: add shade and vegetation, use cooler roofs and walls, preserve airflow, reduce waste heat, retrofit housing, protect electricity, cut pollution, and give residents places to recover at night. And above all, treat nighttime heat as a primary hazard rather than the quiet interval between daytime records. A city that reaches 40 degrees and cools rapidly is dangerous. A city that reaches 37 and remains near 30 through the night may impose a different cumulative form of stress that never allows the body or the built environment to reset. This is the mechanism hidden inside the dramatic headlines. Urban geometry is not weaponizing the atmosphere, and inversions are not suffocating cities by literally sealing them shut. The danger comes from reduced mixing, stored heat, weak ventilation, pollution chemistry, high humidity, and repeated nights without relief. Those processes can be measured, modeled, and changed. Some occur thousands of meters above the city. Others occur within centimeters of a roof, leaf, road, or human skin. Their scales are wildly different, but during a severe heat event, they can align into one continuous chain from the upper atmosphere to a bedroom floor. The invisible ceiling is real, but it is not one ceiling. It is the moment when atmosphere, architecture, and human vulnerability stop releasing heat fast enough to keep a city safe. And in a warming world, the most dangerous city may not be the one that gets hottest. It may be the one that never cools.